In this video I will show you how it might be possible to visualize the time differences when light travels from A to B in one direction, in combination with a constant high-speed movement. In first place we need a light beam splitter, and this shows you my solution of how to split a light beam into two light beams, and back to one. This is how the image of the interference pattern looks like. I will now going to add prisms that could make changes in the speed of light visible. Beam splitter with prisms. First I will show you what I am going to use prisms for. You see here symbolically a piece of glass that I have placed at an angle of 45 degrees. A beam of light will about pass through this piece of glass, as shown. If I divide this piece of glass into two separate pieces of glass, then light will pass through in about the same way. If I now slide the right piece of glass upwards, then the total thickness of both pieces of glass becomes less than before. If I remove the top part of the right piece of glass, and the bottom part of the left piece of glass, then it becomes clear that I can replace the pieces of glass with two prisms. The light beam splitter seen from above. On this drawing, I attach the prism number 2 and 4 to a high-speed up and down mechanism. For a better view and explanation, I move everything within the center line, enlarged to the next drawing. The enlarged view. If I now move the mechanism upwards, then the total thickness of prism 1 and 2 will be the same as the total thickness of prism 3 and 4. In that case the interference pattern will not change at all, regardless of where the mechanism is located. I will explain and show you a test setup, with which I will demonstrate that the interference pattern does not change when I move the prisms back and forth. The test setup. I will show you what's behind this: the lamp, screen, A, and the first piece of glass to split the light. The first two prisms, 1 and 2. The second two prisms, 3 and 4. The second piece of glass to combine the light. Screen, B. The camera, as the eye. And the part to adjust the piece of glass. The image of the interference pattern is going from this camera to this monitor, on where the image with the interference pattern is visible. This part is connected to this part, and they are connected to a wire that runs along the table to a pulley, and from there it runs on the other side along the table to the parts again. The parts can then be moved back and forth by turning the pulley. The test setup in practice. I will now demonstrate that the interference pattern will stay steady in the window when I move the prisms back and forth by turning the pulley. This drawing is an explanation of why the window with the interference pattern on the monitor is moving back and forth. It's because the total thickness of glass is changing while moving the prism. Now the most important part of my idea, explained. Now the lamp has to act as a flash lamp, and this can be done by placing a mechanical shutter with fast shutter speed in front of the lamp, which will be activated by the up and down mechanism. Assuming the arm with prism 2 and 4 moves up and down at 3000 times per minute. When prism 2 moves upwards and reaches exactly this point, the shutter will then be activated. The lamp then acts like a flash lamp through the shutter at 3000 flashes per minute. When this light beam reach A, the other light beam reach A, as well. The light beam will then travel until it has reached B. Light needs time to travel from A to B. In the meantime, the prism with number 4, which was on this place before, has moved up during that time, a little bit. The result that prism 4 has moved upwards will be that this distance is shorter than this distance. Because it passes through less glass than the other, this light beam will be ahead of the other light beam, and the result will make the interference pattern disappear. While the mechanism is still moving at a constant 3000 times per minute, we have to readjust the last second piece of glass to get the interference pattern back. We will then turn the whole device, while still moving at a constant 3000 times per minute, in the opposite direction. If the speed of light in this direction, due to some reason, is different than the speed of light in the previous direction, then there will be a time difference that the light beam reaches B, and that will move prism 4, more or less, which will change the total thickness of prism 3 and 4, and that results in changing the interference pattern by moving up or down. So far, I have only shown an up and down test setup, but I think it is better to build a rotating one. Here you see an example of a rotating one. A short summary of the rotating one, as it is about the same as the up and down mechanism. Slow rotation, interference pattern not moving. Fast rotation, interference pattern disappears. Readjust to get the interference pattern back. Turning whole device in opposite direction. See the link below if you want more information about this rotating, one-direction interferometer. Thank you for watching this video.